Friends, very good morning to everyone. We dealt with the carbocations, its structure, and also the factors affecting the stability of these carbocations. As we know, carbocations are the reaction intermediates which are formed during the course of the conversion of starting material to product. How to prepare these carbocations is the subject of discussion for today's class. Carbocations can be prepared by ionization of organic compounds. In an organic compound, if it has a living group, leave the molecule along with its electron pair, it creates a carbocation. This ionization can be achieved by solvolysis by using a polar solvent. Alkyl halides can ionize to give the intermediate carbocation and an halide anion. This process can be increased or hastened by using a mineral acid or a Lewis acid. If I take Rx, an alkyl halide, it can dissociate into R plus and X minus in the presence of a polar solvent. When I add mineral acid or Lewis acid, it hastens up the process. These carbocations, which are formed, can be stored stably in the presence of fluorosulfonic acid and antimony pentafluoride. The mixture of antimony pentafluoride and fluorosulfonic acid is the strongest acidic solution known to us. These come under the category of superacids. If I add alkyl fluoride and treat with antimony pentafluoride, it gives a stable salt of carbocation R plus SbF 6 minus. These superacids are so strong that even it reacts with alkanes. Alkanes, as we know, they are the most rugged species, most inert species, and they are non-reactive species, which is known to the organic chemist till today. When I heat at 140 degrees centigrade, it converts methyl into methyl carbocation. Even the most inactive species like alkanes can be made to ionize in the presence of these superacids. That is the beauty of these superacids. This formation of carbocations begins with the protonation of methane. Methane, when it gets protonated by the superacid, it gives rise to CH5 plus, which again decomposes to give rise to CH3 plus and hydrogen. And a methyl carbocation is generated. Another method of generation of the carbocations is protonating the lone pair of electrons. As we know, lone pair of electrons is present on oxygen and nitrogen when it is in the sp3 hybrid form. ROH, the oxygen in alcohol is in sp3 hybrid form. It has two sets of lone pair of electrons, and this lone pair of electrons gets protonated in the presence of an acid. Once the hydrogen is added to this oxygen, the divalent oxygen becomes trivalent, and its capacity to bond is only 2 and it has 3 bonds. That's why it becomes positive. Positive in this sense, it becomes electron deficient. To satisfy this electron deficiency, the bond between R and O breaks and it gives rise to R plus, that is carbocation, and water. This is another method of generation of carbocations. We can generate carbocations by adding hydrogens or an electrophile to the pi system. As we know, the pi system, C double bond C, it is pi excessive system. because it is having pi electrons extra along with sigma electrons. The H plus an electrophile. In the presence of an electrophile, the pi electrons moves towards one carbon and that gets protonated. The electrons are shared with H plus and a new carbocation is formed over here. Similarly, with acetylene or alkynes, the protonation can take place and it can give rise to alkene carbocation. We can generate the carbocations by adding a proton or electron file to a CX bond where X is oxygen or sulfur or nitrogen. The protonation of this pi system takes place. The giving rise to an electron deficient X. To satisfy this electron deficiency in X, pi electrons moves, creating a carbocation over here. From other carbocations, the carbocations can be created. If I take an amine and treat with nitrous acid, I'll get corresponding diazonium salt. This diazonium compound, when I heat it, it breaks to give rise to R plus and it loses nitrogen. Non-classical carbocations or bridged carbocations. This can also be generated. The acylation of the bridged molecule, if I take OTS moves away along with its electron pair creating a positive center, the adjacent double bond will move towards this positive center to satisfy a bond is formed and a neighboring group, it acts as a neighboring group and participates and a new carbocation is generated in the process of acylation of this kind of molecules. This type of carbocations are called as bridged carbocations or non-classical carbocations. Overall, we can generate carbocations by ionization method followed by protonation of the lone pair of electrons and protonation of the pi electron system, protonation of the CX bond, and from other cations like nitrogen cation, I generate carbocation. These are the few methods of preparation of carbocations. Carbocations can undergo reactions. What type of reactions the carbocations can undergo? As we know, carbocations are short-lived and they are highly unstable. And it is very difficult to get isolated. It immediately reacts with other molecule to gain stability. It reacts with the nucleophile to give substitution reaction. It loses a proton to give a elimination reaction, or it can rearrange itself to give a new carbocation which is more stable than the original carbocation, and it can add to the another unsaturated rings to give rise to a new cation. It can capture a nucleophile CH2 plus and it can undergo nucleophilic substitution. The adjacent carbon hydrogen gets deprotonated and it can give rise to alkene, an elimination product, and it can rearrange itself. Nucleophilic substitution, if I take Rx alkyl halide, it can dissociate it to R plus and X minus when I treat with a polar solvent. The carbocation which is formed, which is unstable, can react with another nucleophile, an electron-rich species. A nucleophile, an electron-rich species, and the carbocation is an electron deficient species. Both of these attract together as they are unlike poles, and it gives rise to Rz. Starting material I have Rx, the X minus is being replaced by Z minus. That's why it is called as X minus is substituted by Z minus. Hence it is a nucleophilic substitution reaction. It can undergo elimination reaction by losing a proton from the beta carbon. When it loses a proton from the beta carbon, it gives an alkene. The X minuses, which is moved away, give rise to a carbocation, and the adjacent carbon or atom, which is having hydrogen, the bond between the adjacent atom and the hydrogen in it, it breaks, and the H plus moves away, and the electrons are shared with this positive center to give rise to an alkene. And it is something like, if I take this is a carbocation, right? This is a primary carbocation. Adjacent carbon is a beta carbon which is having hydrogen. If this hydrogen is abstracted by using a base, the excess electron are shared with this carbocation to satisfy its electron deficiency, and it gives rise to an alkene. There is another reaction which an carbocation can undergo. It adds up to unsaturated compounds. As I know, CH3 plus a carbocation which is electron deficient, it can act as an electrophile. In the presence of an electrophile, across a multiple bond, what happens? There is an electromeric effect where the pi electrons moves towards one carbon, and this becomes electron rich, and these excess electrons on the carbon bonds with an electron deficient electrophile, and it gives rise to carbon carbon bonding, and once these electrons have moved towards this carbon, a new carbocation is generated. It can undergo addition reaction too. It rearranges itself. Reaction is one if it interacts with another species. If it won't get any other species, it has to get stabilized. Somehow it rearranges itself to become more stable than the original carbocation. The rearranged product may not be completely stable, but definitely it is more stable than the original carbocation. In this, a alkyl group or an aryl group or an hydrogen along with its electron pair migrates from the adjacent carbon to the electron deficient carbon, and it gives rise to a more stable carbocation. Here, if I see, this is a carbocation which is formed, and this is a primary carbocation. The hydrogen, along with its electron pair, it moves towards this carbon to satisfy this electron deficiency on the carbocation. H, along with its electron pair, is called as hydride ion. The hydride ion from one position shift towards two position. That's why it is called as 1, 2 hydride shift. Once this hydride has taken its electrons and moved towards this electron deficient carbon, the carbon from which the electrons are taken away, it becomes electron deficient and is a tertiary carbocation. A primary carbocation has got converted into tertiary carbocation by 1, 2 hydride shift. And we know tertiary carbocations are more stable than primary carbocations. This rearrangement occurs when it do not get any other species to react. This is comparably more stable than the original carbocation. Always molecules tend to stay in the most stable form. That's why this reaction occurs. The instead of hydride, that can also give rise to alkyl shift. Alkyl group along with its electron pair it shifts, it gives a secondary carbocation. This carbon is attached to two carbons. That's why there is a carbocation attaching to two carbons. That's a secondary carbocation. Here, this is the carbocation attached to three carbons. That's why it's a tertiary carbocation. And we know that tertiary carbocation is more stable than the secondary carbocation. That's why 1, 2 hydride shifts prefers over 1, 2 alkyl shift. Instead of alkyl or hydride, if there is an aryl group, then aryl shift can occur. This electrons, phenyl group along with its electron pair moves towards the electron deficient carbon to give rise to a new carbocation. Is a secondary carbocation. Hence, it gains comparably more stability. It can undergo four types of reactions. One is the nucleophilic substitution reaction, another is elimination reaction, and an addition reaction or a rearrangement reaction. These are the four varieties of reactions an carbocation can undergo. Next class will be dealing with the different types of rearrangements a carbocation can undergo. Till then, have a nice day. Thank you.